started, and let's see. We had some presentations last week, and I guess you guys did a pretty good job, and I'd like to present as good as you guys. Let's see. Before that, we ended talking about YOLO. Actually, we looked into several applications, computer vision applications using CNN, and in particular, we looked into the object detection problem, and we mentioned about YOLO, and then let me just go to YOLO. So as you remember, oops, it took me a long time to get to. I should reorganize the slides really. So we mentioned that if we go from the classification to the detection problem, the biggest issue there is that we don't know how many objects are there inside the image. So we may have 2 dogs here, 2 dogs and 1 cat, and maybe we have more cats and dogs. So in classification problem, so since we don't know how many objects are there, it's hard to do, kind of do regression directly. But a workaround with YOLO or SSD is basically we don't care about it anyway, so we just split the image into many tiny patches, and for each patch we're trying to say that would be say we will assume there could be 1 object there, or so, and also we assume that the object can have different shape, in the sense maybe the object, maybe for this patch here, the box of this dogs here eventually be kind of a tall box here, or instead of a wide box here. So basically we just have different kind of boxes here, and then for each of these boxes we're trying to do a classification inside the box, and also trying to do the regression. And of course we don't what I mean for each of the box, it doesn't mean that we first partition into pieces and then do a CNN for that, and then do a classification regression. But instead, everything is done in one big chunk. We start the host, have a CNN layer, starting at the beginning, and then afterward do classification and regression for each of the regions. And that's YOLO's. And by the way, it's already version 3 now. So have a version 3 just came out, I guess 2 weeks ago, more or less. Yeah, and basically if I briefly look into the paper, so they mentioned that that they are still not as good as the RCNN that I mentioned later on, the other approach, but they basically are as good as SSD and also much faster. So so today I will look into a different approach here. It's actually the original approach. First kind of I would say first successful solution to do object detection. So what they did here is known as the RCN, and so basically what you can imagine is, okay, the most likely way to do this thing maybe we have an image here, we're trying to recognize different objects here, maybe dogs and cats, or different objects here. So we can do a sliding window approach, right? We just slide the window, and then for each window we do a CNN, basically just an object recognition. So hopefully if we're able to recognize something, then there's something there. But the problem is this approach will be really slow, and therefore it's basically no one even I think someone tried this, but it doesn't work. It's just too slow. So immediately, the first more successful work is, as I mentioned, the RCNN. The R is basically referred to region proposal. So what they did is like they borrowed some long algorithms in computer vision. It's not something related to like neural network and deep learning. So basically, some long computer vision algorithm is trying to look for region of interest. So basically, you have an image. It will give you a bunch of region proposal. Basically, you expect that there can be some dogs or cats or some objects there. So then afterward, they just basically do exactly the same thing as I just mentioned for each of the region proposal, trying to recognize something, whether there's a cat or dog or like anything. So therefore, you have an image. You go for each of the region proposal, and typically you get like about 2,000 different regions. And for each of the regions, because we do CNN, and as you know, we expect the input size is the same, so we just first do a warping to the same image size, and then like just go for the conflat, and then like what they did, they just use a SVM classifier to classify like if there's an object or low object, or like what kind of objects would that be. And then they also have another kind of head here. It's like a regressor. So it's a refinement of this box here. So you have originally have this region, but maybe this region is not accurate. For example, you have this, looks like there's a man here, but it looks like it skipped this shoulder here. So this regressor is supposed to correct this problem and then just adjust this box, the orientation, not orientation. I mean no rotation. It's just the translation and also the width and height there. And that's basically it's not too far ago. It's just 2014. It's like by Gerson. And then later on, actually, first let's look at some of this problem here. Actually the apparent problem is very similar to the sliding window. Is even though we don't have as many windows as we need to try in the sliding windows maybe, but still like we have lots of region proposal. Like we have 2,000 of them. So it takes just lots of time. And not just lots of times, we also takes lots of space because you need to like pull out all these as input images, and then like storing each of the output layer to expect. Basically like actually most of the space consumption is the input here. So it turns out it will be really, really big. And I don't know if we have a number here. I forgot. Like it's just like if you basically like if just for training, I'm not sure what kind of computer they are using, but it takes like 84 hours. It's quite a lot. And also like maybe more problematic is like detection is not fast also. Because maybe we can afford like training to be slow. It doesn't matter, right? Once you train, we just put it into a cell phone, and we have apps there to just detect object in whatever you take a picture there. But even for detection, it's pretty slow. Like it takes 47 seconds for an image. So definitely you cannot do any real-time application there. So and then like there's a fix there like called SPP-LET, but I won't go into this one. Instead, like we'll look into like so-called like fast RCNN. Is what it does is actually pretty lateral. The problem of this computation, like space and time consumption, is mostly because for each of the region proposal, we just treat that as an individual image. And then we compute all this CNN again. But as you imagine, if I have one vision proposal like this, I have another vision proposal like this, there's lots of overlap of computations here. So basically, all these visions supposedly is computing the same thing. So therefore, instead, the idea is maybe we can just do one big conflict in the entire image first anyway, and then afterward we compute the vision proposal of the image, and then we map back what supposedly the vision proposal corresponds to in the transform image in the by the conflict, and then in this layer we will just process this. So we don't need to compute lots of different conflicts for each of the vision proposal. We just compute one big conflict. So this basically saves lots of time. Then again, basically here, because we already have conflict here, so we of course we can do swapping, but more lateral way we will just do a kind of polling, right? So it's very much similar to mass polling, just this will be irregular. So maybe some of these patches inside the region will have a little bit bigger, some is smaller, and so on during the polling. So then afterward, more or less it's just the same. Then you have some fully connected layer, and then trying to do regression. So we have a big one. So for each of these, trying to do classification and also trying to do regression. So for each of these, so therefore that would be, for example, I have 2,000 vision proposals here. So therefore there should be 2,000 outputs here for each of the classifier here, and also of course we also want to have the bounding box regressor just to adjust to refine the location of the object. So any question here? So it's kind of amazing. You look at this is 1 year ago, and then 1 year later they have something a very big improvement. And then you can combine these two loss functions, right? Then you can basically chain end to end now. So previously it's a little bit awkward actually, because you have I don't want to get into that. So anyway, this basically is end to end, is much simpler. And let's see if I have some time here. Yeah. So if you look at the training time here, so previously for RCNN is 84 hours. Now it's only need to take 8.75, I think is 8.75 hours here. And then in test time it shrank from 40 something seconds to only 2.3 seconds. But then you look into that, in the past, the vision proposal, the step as I mentioned, is just classic computer vision. It's reasonably fast. That you give an image, it will kind of just spell out 2,000 different vision proposals there in 2 seconds. But now if you compare this time used for by this vision proposal function with the actual computation of the network, then this become a pretty significant overhead. We have 2 point something seconds just to compute the vision proposals. So then as you can imagine, the next paper to solve this will be a faster LCNN. So and basically the faster LCNN is anyway we already trying to compute this vision proposal using classic method, right? But we already spent lots of time in this CNN things, and as you know, CNN you can imagine as lots of pre-processing step for computer vision. So we can actually use the intermediate layer to try to estimate the vision proposal, right? So therefore, instead of just use something old in the computer vision community. We just like build from scratch a new vision proposal function here. It's like a vision proposal network, and because this is like this computation is like shared by also like every other things, right? So therefore it doesn't actually take any much time. So after this, like you only have some maybe like fully connected layer or like some other like comp layer, so super fast, and then like you can able to compute this vision proposal. So of course like the only complexity here is now like earlier you only have this classification loss and also this regression loss, but now you also need to have additional loss here, trying to have a good estimate of the vision proposal. And I really cannot go into detail for this one. It's pretty messy, but you may want to look into the paper, and it actually turns out it's quite similar to YOLO also in the sense. And actually that's let's just look at the result. It's basically, if you look into the time, now it's really, I would say like not real time yet. If you want to put it in the real time kind of video application, it's still not real time because per image is like 0.2 seconds, so it's like 5 frames per second. But it's already like much faster than the original, like only 2 years ago. And then of course we mentioned YOLO, and YOLO turns out is even faster. Yes. Yes. Oh, I guess I. Oh, I guess I have the same problem. Benny, I cannot hear you actually. They promised to fix it, but I don't think they fixed it. Let's see if I can. Trying to say it again, like I turn the max. I turn the off.
Okay.
Yes.
Okay.
Barely.
I want to know the performance of RCNN and YOLO. What's better?
Our CNN is still better actually. Actually, I guess like the best reference, I think, of course there's like other reference here, like there's one good reference here. You can look for this Huang's paper. It's a 2017 like CVPR paper. They did a good job like doing lots of comparisons and also like suggest some kind of what's that word? Like some I cannot find the word. Anyway, so how to train this, how to use this RCNN and also like YOLO effectively. But also I will strongly suggest you to look into the new YOLO paper, like YOLO version 3 paper, because they also mention, because that's basically the latest one in this line of work, and they compare with other approaches like faster RCNN and so on. And yes.
Yeah, that is interesting if we compare in between YOLO 23 and RCNN.
Actually, I'm not sure I have the paper here. If I have connection here, yeah, maybe I can even have to always, yeah, here I have the paper that's right. We can even browse the paper now. So I want to kind of like give one note here, like they are pretty in style when they write this kind of paper. Like they have a very different styles of writing, and it's pretty pleasant read here. And let's see. Wait a sec, is that YOLO version 3? No, this is not version 3, I think. Oh, okay, I clicked the wrong link here. Actually, if they let's see, top 10, top 5. Yes, they also compare with the Westlet, and this is actually pretty nice. As you can see, like YOLO version, I think this is the YOLO version 3, and I remember, like, in the paper they didn't mention that it's better than. Okay, maybe here. Okay, I can find the paper here. So let's see. Basically, like here they mention. Yes.
Maybe in the below.
So you can look at some of the results here. So they summarize, like, also these two different main approaches, like when we mention like RCNN and those series of RCNN, like this basically is two stages approach. Like you first have this region proposal, and then like even though like everything is inside the complex, but it's like two stages there. But YOLO is basically one stage there. Yes, like Westlet is still better, the best, like but oh yes, I want to mention, like yes, I sorry, I made a mistake. Did I say like RCNN is better? Like yeah, RCNN is still better, faster RCNN is better, but currently the best result is like Watinalet is like I didn't prepare the slides here, but it's based on like focal cost. And anyway, if you're interested, you can dig into the paper also. So they basically modify the cost function. So the rationale there is they say like it doesn't seem like why YOLO is much worse than like the two stages approach, because in the past, like for example, like YOLO SSD, they are kind of significantly worse than like RCNN. Of course, like, they are talking about before like version 3, YOLO version 3. So if you look at the number, this is use a Westlight or somehow, like, but I'm not familiar with DSSD actually. But if you look at this two, like it's quite a bit worse than faster RCNN. Then like people like kind of pondering like why this is like kind of, because it doesn't look like there's any reason for that. So that's the Watinalet paper. Actually, this paper is also by this faster RCNN guy, like also like Carmen Hay and also Gersak. And basically, they're saying that like maybe because like when you do YOLO, when you do one stage, basically you first like partition the image into many tiny pieces. So then each piece, like, you're trying to detect an object anyway, and therefore like, there will be like lots of negative training data there, because like most of the time there shouldn't be anything, because you don't expect like you have an image partitioned into tiny patches, and for each tiny patch will be something there. Actually, most of the time there should be nothing. But when you have the two-stage approach, you have something more balanced because you have a first region proposal network. So you have something that like it most of the time I have already some object there. So therefore, like the argument is like the problem is not the first portion. Like it's not because of the region proposal, but it's because afterward, YOLO and SSD originally do not handle the the training data kind of fairly. Maybe I would say like because they're supposing there will be lots of training data is kind of negative, so they need to adjust that. And for that, like they adjust the cost function. They call it focal cost in this Retina-Lat. And then like this YOLO paper just came out like I think 2-3 weeks ago, or maybe 2 weeks ago. I don't know. Basically, they also compare with this Retina-Lat, and it's still worse than them, but it's quite compatible. Comparable with like faster RCN and so on. And also, it's much faster. It's like they came it's like 3 times faster or something like that. I think I read something like that. And actually, this I think this paper is like lightweight because like they also many papers like mention like what they did and it works, but they also mention what they did and it didn't work. So therefore, it gives quite a lot of insight. For example, like they also mentioned they tried the focal loss somehow. That's the one that I mentioned, like used in the Retina-Lat. They're supposing to make the Retina-Lat so much better, but somehow it doesn't work. So they don't know why, but somehow it just doesn't work for that one. Yes. So, okay, I guess like this part. Let me just put. How do I get out of here? Oh, okay. So I kind of anyway, like I would suggest you to, if for comparison, you can look into this paper and also the YOLO version 3 paper to get lots of comparisons of different approaches. And I guess like for projects, like you really can start with YOLO version 3, something like it's new, it's pretty good, and yeah, it's actually quite a bit faster than still like the others. So if you especially if you're looking into like real-time applications. A last thing that I like to mention is like instant segmentation. That previously we have like kind of object recognition or like and also detection like with only one object. Then we have like multi-object problems. Now we want to not just in this instant segmentation problem. Not only we want to find the location of the object, we want to precisely segment the objects from the background. And so one it was thought to be a very difficult problem actually, but it turns out like just a paper like last year like by the Facebook research, and actually by the same guys, like all the same guys like Kamen Hay and also Gersak. That's called mass RCNN. It's basically combine what we already have like in the RCNN. So because like in the RCNN, as you remember, they have the convlet to compute the region proposal, and then you have like different layers of convlets to compute like which classes the object is supposed to be, and also to regret the box. And then afterward, like what they are trying to do is simply add now a different layer now. So okay, here is like it used to be like in RCNN we have a one head going out is trying to do classification and also regression for the location of the box, and then like we have another layer like coming out from the intermediate layers that trying to just like what we did earlier to do as we mentioned like 2 weeks ago when we talked about like semantic segmentation. So we just use like this as intermediate the layers intermediate layer as features, and add additional layers trying to predict per pixel whether there is an object or not an object. Basically, it's a foreground or background. So anyway, like this, the whole concept is very natural, but it turns out it's just amazing. Like the result is amazing, and this is the result. And basically, it's very much like ground truth if you think of. I mean, if you look at this, and this image is not clear, but realize that there's lots of tiny people at the back, and they recognize those also. So there's lots of tiny people here, and also like this image here, they have bottles here, and they have like one guy at the back, and they recognize it, and also like able to segment this guy correctly also. So the result is amazing, and because it's like also like compare with like faster RCNN, it's only this additional layer here. So in terms of detection, the whole thing is not taking so much more time. So it's computational capacity wise is comparable to like faster RCNN. So maybe like couple frames per second. Like so it's not real time, but yeah, it's close to real time. And they in the paper they also did one more thing, because they already do regression like, for many different things already. So you can just add one another like branch or one more, trying to let's say do a regression of the now not the with the pose, basically with the location of their joints and something. So then also they did something really amazing here. There's some results like as you can see. You can have each of the students like they got the eyes and nose like very kind of accurate location, and also like the joints and the shoulder. This one I cannot see actually this part is difficult like because part of it is outside the screen there. But if you look at that, it's basically it's all quite amazing. Yeah, and okay, and that's basically what I want to talk about for applications, computer vision applications using CNN. So what I'm going to move on next is maybe start